Hi everybody, welcome back to my channel on Feynman integration. I saw this integral on Michael Penn's channel, so I wanted to try to solve it using Feynman integration. He used a pretty neat technique. I will provide a link to his video in the description, but anyway, I'm going to solve it with Feynman integration. So, hold on. Maybe that's better. Okay. But anyway, I'm just gonna. It's trivial to prove that those two things are equivalent. It's just the substitution x is equal to the inverse tangent of some other variable, and then you get here. So I'm not even going to bother writing out the steps for that. I'm just right off the bat, we're just going to set those things equal. And then since we're doing Feynman integration. We're going to do the normal thing and create a function of t closely resembling our original integral by inserting a t somewhere in the integrand. In this case, it's right here, right in front of that x squared on the on e. There. So that's our function of t. Real quick, note that f at 1 is going to be equal to I, and f at 0 will be equal to pi over 2. All right. So let's take a derivative of f of t with respect to t by using the Leibniz rule for differentiation under the integral sign on this. And what you'll get is this, that f prime of t is equal to the integral from 0 to infinity negative e to the negative t x squared times x squared over x squared plus 1 dx. All you're doing is taking a derivative with respect to t of the integrand. So you get a negative and an x squared added to it. All right, let's rewrite this a little bit. We can rewrite that as f prime of t is equal to negative integral 0 to infinity of e to the negative tx squared dx plus f of t. And I'll let you pause the video real quick and see how I got that. All right, so if you didn't figure it out, what I did is I put a parentheses around that x squared right there, added a 1 inside the parentheses, figured out what that had the effect of doing, which was actually subtracting an e to the negative tx squared over x squared plus 1 from the integrand. So we need to add it back. What we need to add back is plus e to the negative tx squared over x squared plus 1, and that is exactly our f of t. And that's right there. So that can be rewritten that way. All right. So for our next step, we can just go ahead and evaluate that. And I'm not gonna rewrite it on another line. Basically, let's just say that u is equal to x times the square root of t. That will give us dx is equal to 1 over the square root of t du. Right? Yeah. All right. So I know I said I wasn't going to rewrite it, but I'm going to. So f of t is equal to negative integral. Let's see. Our bounds of integration do not change. 0 to infinity e to the negative u squared, and then our dx is over the square root of t du plus f of t. Now this evaluates nicely to negative 1/2 times the square root of pi over t. All right, so let's rewrite it on another line. I can always erase stuff if I need more room. So our f prime of t is now equal to negative integral 0. Nope, I forgot. We're actually just evaluating that integral. Okay, what did I say? This was going to be negative 1/2 times, well, let's write it this way. Negative square root of pi over 2 times 1 over the square root of t. That's what it'll be, right? Because without the square root of t can come on the outside, and that's going to be negative 1/2 the Gaussian integral. That's right there, and there's the 1 over the square root of t, so that's correct. And then plus f of t. And then we're going to say that y is equal to f of t. So we can just rewrite it this way. dy dt and then let's just go ahead right away and subtract our f of t. We'll just bring that to the other side as a y, because y is equal to f of t. And then we will set that equal to negative square root of pi over 2 times 1 over the square root of t. And that is correct. Yep. There's our f prime of t. There's our f of t brought to the other side. There's our negative square root of pi over 2, and there's our 1 over the square root of t. Okay, now what? Now we're going to borrow a tool from differential equations, which is called finding an integrating factor. There are formulas for it when you have first order linear differential equations, which this is a member of. And like I said, there are formulas for finding integrating factors. Basically, the idea is to find some function of t that you can multiply both sides of the equation by, so that on the left-hand side, you will end up with the result of a product rule. I know that was a mouthful, but let's see what happens when we multiply both sides of the equation by the integrating factor e to the negative t. So we're going to have dy dt e to the negative t minus y e to the negative t is equal to negative square root of pi over 2 times 1 over the square root of t. My bad. We have to multiply this side by e to the negative t as well. So we haven't changed the function or the equation. All we did was multiply both sides of the equation by e to the negative t, and it's valid always because e to the negative t will never be 0. So this is as true as that could be. Let's see. Well, so the whole reason we did this was so that this side would become the result of a product rule for derivatives. And this is the result when you take the derivative with respect to t of y e to the negative t. Because the product rule says that the derivative of a product is equal to the first times the derivative of the second, which is right there, plus the second times the derivative of the first, right there. So that is just the derivative with respect to t of this. And we set that equal to the other side untouched. Okay, now what? This is kind of weird, so let's get rid of that derivative by just taking an antiderivative on both sides. So if you take the antiderivative on both sides, on this side you'll just get y e to the negative t. And on this side, well, you just get this. Does that help us? Not really, not yet. It does, but it's hard to see how it does at this point. Well, let's think. How could we rewrite this? Well, that is exactly this. If you took the antiderivative of that function of t, you would get some other function of t plus a constant of integration, right? So it could be rewritten like this. We could just say that this is the integral from some constant c up to t of e to the negative x dx over the square root of x. I hope you all agree that that's equivalent. This is just another way of writing the antiderivative of e to the negative t over square root of t. Because you will get the antiderivative evaluated at t plus or minus a constant of integration. All right, so we've rewritten that. But now we need to get rid of this c somehow. We need to find out what that c is going to be. Well, we don't really find, that's a nasty place for that c to be. But let's just see what happens if we use the standard techniques. We know that our function of t evaluated at the point 0 is equal to pi over 2. So let's plug in 0 to this and just see what happens. So if we plug in 0 for t, on this side we would get pi over 2 times e to the negative 0, which is just 1. And that would be equal to negative square root of pi over 2 times the integral from c to 0 e to the negative x over square root of x dx. I probably should have done this substitution in the last step, but let's just see what happens if let's make the substitution that x is equal to v squared. That'll give us dx equal to 2v dv. Let's make sure I've done everything right up to this point. We were plugging in 0. That'll give us pi over 2. That part remains unchanged. The c stays. T goes to 0. This remains unchanged. Now we're going to make that substitution. All right. So now we have pi over 2 being equal to negative square root of pi over 2 times, let's see, the integral from, let's see, we're going to get the, v is equal to the square root of x. So we're going to have the square root of c. Whatever, I'll just write it. I probably could just write c. And then our upper bound is 0, so our upper bound will remain 0. And then we have e to the negative v squared. E to the negative v squared. I have to be very, very careful. All right, and then we're going to have over v times dx times 2 v dv. All right, let's do some manipulation. Let's get rid of this negative sign to switch the bounds of integration. So we'll get 0 square root of c. It's probably not necessary that I'm putting that square root there. In fact, I'm sure it's not, but I'm just going to do it. Okay. This v and this v cancel. Let's see, this 2 and this 2 cancel, giving us just a square root of pi. Bring that dv over here. Okay. So divide both sides by the square root of pi. Okay, so this is how we're going to find our c. We know that the integral from 0 to something of e to the negative v squared dv is equal to the square root of pi over 2. C's got to be infinity, because we know that the integral from 0 to infinity of e to the negative v squared dv is equal to the square root of pi over 2. So we have found our c is equal to infinity. All right, so we have found our c, and it is equal to infinity. That's not something we usually like to get for a c when we're trying to solve these sort of things, but you know what? We're just going to trust the math and just keep going with it. All right, so now we're going to utilize our c being equal to infinity on this part right here. So we have y times e to the negative t is equal to negative square root of pi over 2 times, let's see, right away I'm going to switch the bounds of integration by getting rid of that negative sign. So this will become the integral from t to c, which is infinity, of, let's see, oh shoot. I really should have done that substitution there. Well, I'll have to go with it. So, oh boy, no, we're gonna have to do a redo. Sorry, guys. V is equal to, v squared is equal to x, dx is equal to 2v dv. I have to be careful. All right, so we have y times e to the negative t is equal to negative square root of pi over 2 times the integral from square root of c to the square root of t, e to the negative v squared over v times 2v dv. This v cancels with that v. This 2 cancels with this 2. Negative square root of pi, and yeah, there we go. That's it. All right, so now, let's see, this is negative square root of pi. Yeah, that's better. Okay. So now we need to get rid of this c, and I'm actually just going to write it as a c. Yep. Okay. That's good. All right, so now we're going to find our c by plugging in 0 for t. So what we get is that pi over 2, that becomes our y when we evaluate the function at the point 0, times e to the negative 0, which is just 1, and that's going to be equal to the square root of pi times the integral from the square root of 0, which is just 0, up to c times e to the negative v squared dv. Is that correct? That is correct. Dividing both sides by the square root of pi, we get that square root of pi. Oops, I'm sorry. Yeah, square root of pi over 2 is equal to this. making it necessary for C to be infinity for that function to hold, for this to be true. C has to be infinity. So we'll just write that down. C must equal infinity. And like I said, that's not a great thing to end up with for C. Well, let's just see what happens. So now we have that y times e to the negative t is equal to negative square root of pi. Let's get rid of that negative sign and switch the bounds. We're going to have square root of t to infinity of e to the negative v squared dv. Yeah, that's exactly this with, yeah, no, that's it. C has to be infinity, so this is our new function. All right, now, we know that the answer to our equation is equal to f of t at the point t is equal to 1. So let's just see if we can solve this right now by plugging in 1 for t. What's that going to give us? Well, if we plug in 1 for t here, we're going to get, let's see, our function evaluated at the point 1, which is just I, because, yeah, okay, so we're going to get I times e to the negative 1, which is just write that as over e. That's going to be equal to, let's see, square root of pi times the integral from 1 to infinity of e to the negative v squared dv. This is almost the complementary error function right there. What do we have to do to that to make it the complementary error function? Well, we need the square root of pi on the bottom. So let's divide both sides by pi. And then, okay, so we'll get pi here, and then we'll get pi here. And that will just give us 1 over the square root of pi. 1 over the square root of pi. All right. But now we need to multiply both sides of the equation by 2. And we have that. And this is ERFC of 1. So, that gives us I being equal to, let's see, we're going to have pi e over 2 times ERFC of 1. And that's it. That's how you solve that using Feynman integration. I hope that wasn't too bad. I just thought that was neat that you know, a lot of this is very similar to my last video, which is why when I was watching Michael Penn's video, it kind of stuck out at me that this might be doable using Feynman integration, and it is. So there you go. Hope you enjoyed that.